Australia, Switzerland, the UK. She was here as well as a postdoc for some time, and now she's in Madrid, assistant professor at the Autónoma University. And she's going to talk about some of the timer stuff that we have been working here during this week, and some of the papers that are already out. So.
Right. Well, yeah, I'm gonna tell you a little bit about the project Timer. We've been this week gathering together. The project is just starting, and so I'm gonna show you some results that have been published already. But what I want you to take is that this data set have a lot of potential, no, for a lot of different applications, mostly related with the issue of this galaxy formation. No? Despite I'm giving this talk here, the PI of the collaboration, well, I'm not the PI of the collaboration, the PI is sitting there, is Dimitri Gadotti. Obviously, he's much smarter than me, because last night he was having dreams what I was putting slides together. Most of the work that I'm presenting here is being done by the people here. I highlight in red the ones that are here in this room, so you can ask questions. And well, I'm going to tell you what it's all about. No? The Timer project, the data set consists in 24 nearby bar galaxies. They are all like, the average distance is 20 megaparsec. And we are observing them at the BLT using MUSE, which is an integral field spectrograph covering the optical part of the spectrum. The spaxels are really small, so the spatial resolution is very high, although we are not observing with adaptive optics, so we are limited by the same. The sample has been selected to be bar and to have features that we think are produced by the bar, like inner rings, inner disk, features like that. We use for that the morphological classification by Ronald Buta using the S4G catalog. The green squares here mark the field of view of MUSE, which is 1 arc-minute per 1 arc-minute. So we are actually just sampling the very central part of the galaxies. The goal is understand this galaxy formation, as I mentioned before. We think that during the life of this galaxy, there's like 3 different stages. In the first one, mergers are very common. Then there is an epoch where there is merger maybe become less common, but there is a lot of gas accretion. And so these galaxies, there's already a disk, no? But the disk is very clumpy. If you measure the velocity dispersion of the gas, it's very high. So the disk is not really dynamically cold. And then after a while, well, the gas accretion starts to lower down. Then a massive disk, dynamically cold, can form. And when it forms, it can evolve mostly due to internal processes. So when a disk is massive enough and is dynamically cold, bar appear very quickly. No? It's very easy that this instability happens. And gas are believed to be like one of the most important catalysts for this further evolution in the disk, no? For these morphological transformations since the epoch where the gas accretion started to be so common. So bars produce these tangential forces that produce the gas to cool and fall down to the center through these dust lanes. And there, the gas can form inner disk and inner rings as well, depending on the position of the resonances of the bar. So what we want is to study these inner features, inner rings, inner disk, that in principle can only form when the bar is already formed. That's it. That can only form when the disk is dynamically cold and mature. So by dating these structures like this and inner disks, we want to mark the epoch where that mark the transition between this accretion-dominated epoch to this internal evolution epoch. So in some cases, it's easier than in others. But well, apart from that, we can do a lot of other stuff with the data set, and we can study the influence of circular evolution and the properties of other structures. For example, we are seeing in some of our galaxies these bars between bars, inner bars. This is an example of the galaxy 1291. This is the main bar of the galaxy, and here there is a little inner bar. And here you can see they are oriented with different position angles. No? So the inner bars are very difficult to observe because normally you have dust in there because they are easily confused with inner spiral arms, for example. But they probably are very important to funnel the gas towards the very inner parts of the galaxies, where the central black hole is. The problem is that we know very little, because, as I told you, they are very difficult to observe. But as I'm going to show you later, we are making some progresses. Classically, all these inner rings, inner disks, inner bars are things that are going to increase the luminosity over the extrapolation of the exponential disk in the galaxy. No? So some authors would call all these pseudo bulges, as opposed to classical bulges that they are not related with these structures. No? Another type of bulge that we find in galaxies are actually like bars. No? These are the boxy peanut bulges. Our galaxy, in fact, has some of these bulges that they suffer another instability, a vacuum instability, and in the inner part they get thicker, and they form these boxy peanut bulges. So our sample is low inclination galaxies, so it's very difficult to see these boxy peanut bulges that are more easily seen edge on. But we are going to use some kinematic indicators of his presence. So this is a work by Victor de Batista, where he ran several simulations of bar galaxies. Some of them form a peanut bulge. And he plotted here the H4, that I will explain what it is for the student now, as a function of this is the center of the galaxy, and that's the radius. And what he's seeing is that when the peanut develop, there is some minimum in the H4 parameter. That doesn't happen in those galaxies that do not develop this boxy peanut bulge. So what is the H4 for the student? So normally we parameterize the line of sight velocity distribution with a Gauss-Hermite series that is here. So the first term is just the velocity, the second is the velocity dispersion, and the higher moment, so deviation from this perfect Gaussian term of the velocity distribution of the line profile. So the H3, so a symmetric deviation from the perfect Gaussian. So an H1 that is negative will solve like an asymmetry towards the left, like a left tail, and the opposite for an H3 positive, and the H4 show you the deviation from that are symmetric. So an H4 that is more like I don't know how to say it. It will be positive, and one that is more pointy will be more negative. And why I'm saying this, because this type of higher order Gauss-Hermite coefficients can serve us to see if we have different components along the line of sight. For example, this is I took that from a simulation of Joseph Barnes, and here you have a kind of a bulge time component with little rotation and a lot of velocity dispersion, and a disk with more rotation. So the final profile is asymmetric both. We have a left component in the H3, and also it will have a pointy H4. We have a higher positive H4. So the correlation between these coefficients and other parameters that we can measure can give us indication of what we have in the galaxy. For example, if we have a disk, we have an anti-correlation between the velocity and the H3 parameter. When we have several components along the line of sight, we normally have like maximums in H4, no? As I was saying before. Or a bar normally stand out as with a positive correlation between the velocity and H. So with all that, because we can take the stellar properties, the kinematics, the gas properties, the kinematics, the stellar population, the gas abundances, we can actually obtain a lot of information about the galaxies we are observing. So this is a quote from Dimitri, from our PI, that say that galaxies are ghostly, we can see through them. Projections of different components complicate matter, but linking different aspects such as structural analysis, kinematic, stellar population, ages and metallicity, ionized gas, chemical abundance, etc., can be revealed. And what I want to show you is that this is true, no? That well, we are still starting, but I'm going to show you some snapshots so that this is possible. So the main goal, as I told you before, was estimating the epoch of this formation, as the epoch where these galaxies settle. But we can also, we want to also understand the real importance of circular evolution, how much mass is actually built up by these bars, no? As opposed to other mechanisms. We want to understand the formation of inner structures, inner bars, inner rings, inner disks, lenses as well, no? That we know later about them. We can also quantify the gas accretion history of the galaxies, and I will show you that we can also put constraints of the feedback mechanisms in these galaxies. So here's an example of a kinematic map for one of the galaxies, the first one that was observed, 4371. This is the velocity map, the velocity dispersion, and the H3 and H4 parameters that I explained before. So this ellipse here marks the photometrically described inner disk. So you can see that the inner disk rotates higher than the main disk. They are decoupled. They have lower velocity dispersion. They saw an anti-correlation between the velocity and the H3, as I told you before, that indicates that quasi-circular orbits, high rotation. And the H4 is also very high, which is indicated that actually, yeah, you have several components there. No? You don't only have the inner disks. The inner disks stand up when we do maps of the angular momentum. And well, this is a zoom here, but you can see that the inner disks rotate faster than the main disk of the galaxy. No? They are a separate component. We see these structures in almost all galaxies of the sample. No? And yeah, to make just a summary of what I say, in most of the galaxies we see that the inner disks have a high velocity and low velocity dispersion near circular orbit from the velocity H3 anti-correlation, and they are separated from the main disk of the galaxy. So how do this looks like in the stellar population? I'm only going to put some examples. We have many more galaxies, but I don't have time to describe them all. So those are the maps of ages and metallicity for 3 galaxies, for NGC 1097, NGC 4643, and NGC 4379. In the map of metallicity, we see in almost all the galaxies as well, very high metallicity in the central parts, no? That we had to understand, so what is that for? In the map of metallicity, take these 2 galaxies here, for example, they show like very old ages. So the inner disk, this inner disk that is decoupled from the main disk is very old. It doesn't stand out as a youngest component. No? In fact, if we look at the absolute ages, no, we cannot extrapolate from absolute ages to residues because there are some issues with the 0 point of the stellar population models. But more or less is older than 10 gigayears, which will indicate that if the inner disk has formed by the gas, no, by the flow of gas to the bar, then the disk was mature, or was there and was massive already, like at 1.5, 1.8. I received 1.5, 1.8, which is much higher resin that it was thought, no? Or that is predicted by numerical simulations. Then there is this other galaxy, NGC 1097, Here in the map of age, we see that these galaxies have a very young inner ring. No? The age in the ring is much younger than the center and than the rest of the disk. This is probably because this galaxy is interacting with another galaxy, with a small galaxy that is providing with the gas to form the disk that form stars. No? Something that you can see here is that the metallicity of this ring is also very low. So the gas is actually coming from this interaction. It's not coming from inside the galaxy. And another thing you can see that the gas doesn't reach the center. It stays there orbiting in the ring. No? So the inner ring resonance actually provides a very effective wall. No? So that's probably highlight the importance of these inner bars, no? To provide this final torque for the gas to reach the black hole inactive galaxies. I don't know if I want to say that. I can ask it. Well, so another thing that we can do is to study the non-circular motions, of the non-gravitational motions in the interstellar medium. No? So here is the map of the velocity in H alpha in emission. So this is gas now. And this is a model, a GEANS model, dynamical model, that takes into account the gravitational motion. And in the right part of the slide, it is the residuals. No? So you can see here the streaming motions that mark the gas that is going to the centers through the leading parts of the bar. No? So we can actually try to start to quantify the amount of gas that is growing, the velocities, etc. No? And learn something about all these gas acquisition processes in the galaxy. I'm not going to say much about that, but I showed you just maps of ages and metallicity, but we don't only obtain like mean ages and metallicity, but the whole star formation histories. So we can start to quantify the star formation histories in the different components, in the rings, in the bars, etc. No? This is thanks to the superb spatial resolution that we have in this data. No? Something that is curious, or I wanted to mention, no? This is an individual case of NGC 4371. This galaxy is a lenticular galaxy, which is very close to the center of the Virgo cluster. And if we do a photometric decomposition, we see that it has several components, which are a disk, a bar, a ring, and an inner disk. Okay. But this galaxy doesn't seem to have any sign of a classical bulge. No? Classically the film. This galaxy is one of the ones that I was showing you before that have an all inner disk. Okay. By the way. In any case, classical bulges are believed to form by interactions with other galaxies or either by the coalescence of giant clumps in primordial disk galaxy. So they are believed to form in this previous period to the secular evolution of the disk. No? And it's difficult to understand how this galaxy that is in the center of the Virgo cluster, no? And that also is a lenticular, which is believed to, they are believed to have classical bulges, have escaped to these processes and have managed to not have a classical bulge. Also, this is like the, I don't know how to say, the textbook properties of pseudo and classical bulge that you get in conferences. No? So our galaxy will be here because it doesn't have an spheroidal or elliptical like a structure. It has flatter shape, spiral structure, and nearly exponential brightness profile. But opposite to what is said here, it doesn't have an starbook or a young population in the center, but it has an old component. So I'm saying that to forewarn you about this very simple picture that we have in mind of pseudo bulges and classical bulges and how do they relate with other properties of the galaxies. No? Here we can start to look very into the details of all the different cases, but we are already starting to find very clear cases that are against this picture. Well, Justin Newman, one of the students here, is doing a study of stellar populations along the bars of the galaxies. There are very few studies that have studied these properties of the bars because it's difficult. but he's obtaining a first sample of galaxies now. This is the H alpha distribution in the sample of galaxies he's studying. So you can see that you have H alpha emission in the rings, in the center, in the spiral arms, but you don't get star formation along the bars, any of the bars that is our sample. No? If you go to study to the stellar populations properties, what he's seeing is that in general, bars are older than the main disk, okay? And they are also more metal rich. This has several implications. The first one is that, well, the bars didn't form recently, no? This is something that is becoming more and more evident, but still there's people who think that bars are continually formed and destroyed, formed and destroyed. But we are finding that all of them are older than the main disk, which means that at least they had to be that old, no? The age difference between the disk and the bar. And another thing is that they are also more metal rich than the disk. No? This implies, no, that when they form, they have to have some star formation as well. Either that or the disk is accreting primordial gas, which is not being recycled. No? But you have to produce this difference in metallicity. No? So all these studies are going to give a lot of information about the processes that form bars, etc. Well, I told you before that we are also finding inner bars, so we are also studying the stellar populations in the inner bars. This is from the work of De Lorenzo Cáceres, Adriano. You see here the age and metallicity maps for two inner bars, the ones in NGC 1291 and the one in NGC 5850. What he's finding is like for this galaxy, the age of the inner bar is older than the outer bar and this part of the disk, and it's also more metal rich. While for NGC 5850, the inner bar is also more metal rich, but it's younger. No? So it's very interesting because, well, combining with other things, he's for the first time putting some constraints, no, to the formation scenarios of inner bars. Up to now, two main scenarios have been proposed for the formation of these structures. In the first one, you have that the gas flows towards the center from the main bar. The gas flows towards the center, form a gaseous inner bar that then form stars. These bars are dynamically unstable, they don't live for very long, and they are necessarily younger than the main bar. Always. In the second scenario, it's basically the same scenario that is playing in main bars. It's like the gas flows towards the center, form a disk. When the disk gets dynamically cold and mature, it can get unstable to the bar formation. So the fact that he's finding all populations in one of the bars is telling you that at least this galaxy didn't form by the first scenario, has to have formed from the second, no? But also using the data that has been from another galaxy and the study of the stellar population related with other properties of the galaxy, she convincingly can say that the inner bars forms like the main bars, no? Like by the first forming an inner disk that get unstable to bar formation. Well, not only that, Jairo Méndez Abreu found for the first time, no, using timer data, that these inner bars can also form peanut bulges. So I showed you before at the beginning of the talk, you remember, with the simulations by De Battista, that you can distinguish a peanut bulge when you see it face on for some minimum in the H4 parameter, which are here. And yeah, he saw it clearly. They made a movie that I'm gonna play. This movie didn't. So the main bar, the inner bar. And the inner bar, which is also a peanut bulge, a tiny peanut bulge. So yeah, this was the first evidence that these inner bars can also buckle, which also reinforced the fact that these bars has formed from inner disks, no? That has to have there some time and be stable to then being able to buckle. Well, another thing that that these studies are showing is that I told you before that it's very difficult to observe inner bars, no? Because you have dust, spiral lamps, and it's really photometrically very difficult sometimes to distinguish the presence of an inner bar, no? But the Lorenzo Cáceres is seeing more and more. Well, he saw it in previous studies, but now he's showing it more clearly even that this inner bar can be characterized by the presence of two minimum in the sigma profiles, what they call sigma hollows. No? So this is the velocity dispersion map of two of the galaxies with inner bars, and you can see the minimums at the end of the bars that are very clear. Okay. So this might be a way to identify them in the future. So like a summary of the double bars, they form from dynamical instabilities of this, and they can buckle like ordinary bars. This, I didn't go into the details of this because it was complicated, but the star formation suppression enhancement is the consequence of the inner bar strength, the momentum of this formation, and the inner bars are revealed through the sigma hollows. I'm going to end up showing you an example that Brian Lehman is doing, trying to quantify the stellar feedback in one of our galaxies in NGC 3351. For that, he uses the maps of ionized gas and stars from Timer and combined it with Cabal data from HST and from ALMA. So NGC 3351 is a galaxy which is around 10 parsec and has a ring where the star formation is very high. Okay, so the star formation is 0.6 solar masses per year only in the ring. Francesca Facuti, also part of the Timer project, made a simulation with a potential tailored to this galaxy, and he couldn't explain the presence of this arc. No? So you have these dust lanes, which are in the bar, no? They are marking the leading part of the bar, but this arc, it was impossible to get like dynamically. No? So within this arc is the consequence of a stellar feedback that has pushed the molecular gas towards the external part of the galaxy, no? Creating like this cavity. So here you can see the H-alpha map, and you can see already like these filaments, no, that the ionized gas is expanding away from the ring, no, and it's bounded to this cavity, no, to where the molecular gas is. So it's probably in favor of our scenario. Here you have the velocity dispersion of the H-alpha and the residual velocity once we subtract the circular motions. You can see here, yeah, like higher velocity dispersion in these areas, which probably indicate these bubbles, no? Regions of more turbulence due to this stellar feedback. And when you subtract the circular motion, you also see like the blue part here, or gas coming through here, and the opposite in the other side of the galaxy. So indicating that this gas is moving in the right direction, no? Away from the ring. We can do emission light diagnostic to see what is ionizing this gas. And in the ring, obviously, this is a star formation. But in the external parts of the cavity, the emission line radius are compatible with being shock, ionized by shock. So everything goes in the right direction. No? We also did an analysis of the stellar population, because with this, I'm going to speak again. Well, this is again the galaxy. The contours mark the residual velocity of the H-alpha that I showed you before. No? So this is gas that is coming toward us, and the other one that is going in the other direction. Okay. So we think that the stellar feedback produce the push, and then successive star formation is maintaining this heated. No? So this, in this case, this part of the ring will be like older and that younger and that younger, no? And ionizing the different cells of the gas that we are seeing. We did an extrapolation analysis of these regions, and we actually get something that is consistent with that. No? Like this region is slightly ordered than this and this. No? And time life corresponds to what we measure with that. I mean, I invite you to read the paper because it's there is a very exhaustive analysis taking into account everything, no? The velocities, the dynamics, what we expect from the energetic, etc. No? And everything seems to be consistent. So with the velocities, for example, we derive kinetic energy of 8 times 10 to the 52 ergs. And using Starbus 99 and the measured star formation rate, there is a way, doing some assumptions, to disentangle which different type of feedback is contributing to this final momentum. No? So it seems that in this case, the dominant mechanism is the direct photoionization pressure. So, well, the take-home message is that the stellar feedback can have a substantial effect on underlying gas morphology, and that we can measure this in our galaxies. No? So the next step will be to see if we can find some trends as a function of other properties of the host galaxies, no? or the environment where they are. So this is some example of the things that we can do, no? These maps of this region. For example, this galaxy has a region which is photoionized by AGN, and it has some photoionization by SOX as well, and the rest of this is star formation. No? But if you look into the O3, for example, you see an outflow in O3. No? So we will be able to study all these things. And I don't know how, if it was very fast, I don't know, was that? Well, but that's my summary, no? As I told you at the beginning, the take-home message is that the MUSE data could constitute a very rich data set with which a number of important astrophysical questions can be addressed. And some of the investigations that are being currently conducted by the TAMR team include the dynamical stellar populations of nuclear bars, normal bars, inner disks, inner rings, the star formation desert in bar gases, and the sun, understanding what is this. The connection between box peanuts and barlenses as well. We are studying also the stellar populations there. The understand the importance of stellar migrations in these galaxies, locations of the nuclear rings with respect to the inner limb resonance or no, to see if actually all the rings are located there or no. Study the zeros and SOC along bars, the excitation stages of the ionized gas also in the stellar medium, and the IMF across galaxies. But also, I mean, we have ancillary data, at least 1/3 of the samples so far is also observed with ALMA, so we can think of a lot of other studies to be conducted. That's it. Thank you.
You, Patricia. So questions? No questions?
Hi, Patricia. I was wondering, in the simulations you presented from Victor de Batista, basically they do some simulations and they find that whenever you have this box of peanut shape, then you end up getting these non-Gaussian shapes. But my question is how degenerate that can be. In other words, can you have another dynamical situation where you can get similar types of this non-Gaussianity?
I mean, you can get a lot of, yeah, but the thing is, where do they get them? I mean, because you get two minimum. It's not just that you get an H4 that is different from, it's higher or lower than 0, but it's that you get them you get these two minimum, no? So I don't know another morphological feature that can give you.
So did they consider in their work whether there could be like other alternatives that would be not very contrived that could end up leading to those types of profiles?
I'm not aware of any other thing that could produce the same, but we haven't looked into that, to be honest. But I can't imagine another thing that can give you the same two minimum.
There are lots of degeneracies. After all, you're looking at non-Gaussian extensions.
Yeah, it's true. I mean,
velocity
an H4 which is negative can be produced by a lot of things, but two minimums, and you also have to. I mean, this is for low inclination galaxies, no? And you also need to know that the backlink normally is produced like 1/3 in the inner 1/3 of the galaxy. So you get these two minimum and at the right distance compared to the length of your bar, I guess you can be convinced more or less that is due to the backlink of the bar.
It doesn't really answer your question, but these simulations are very simple, right? So they start with a pure disk, pure stellar disk, and let it evolve, and then it develops a bar and a box spin on its own. So, yeah, I agree with you that it's difficult to see these signatures. If it's asymmetric, right? Yeah. But so my point is that the simulation is very simple, so it's it's kind of difficult to see why you would see these asymmetries.
No, but what he's saying is, yeah, here they are produced by that, but in the real life they can be produced by something else.
Ah, right. Yeah.
More questions?
I was wondering, you just showed the age and metallicity of the bars. What about alpha enhancement? Because I'm asking, because how do you conclude that bars are old structures just with age and metallicity?
No, I'm not concluding that bars are all structures just with ages, because it's true that bars come from all stars that are already in the disk. Okay? That's what we are using the inner disc, inner rings that are produced when the bar forms. No? That's our clock, not the age of the bar itself. But it's true that the fact that the age of the bar is higher than that of the disc at the same distance is telling you that at least it has this age difference. At least. To answer the alpha over phi, I think we are getting alpha over phi similar to that of the disc, no? Justice? Alpha over phi in the back. I mean, the people who have done the work that I presented, it's all there. So you should direct your questions over that.
Any more questions?
Yeah, hi, Patricia. Yeah, I was wondering, do you have ALMA data for the rest of the sample? Because this study of the feedback's really cool, right? I mean, if you can start trying to separate into different components the contributions to the feedback and the total energy budget, I mean, this is really nice stuff.
Yeah, that's the idea. We have 7 galaxies so far.
7, okay. So, Ryan, are you going to analyze all 20 galaxies in the same detail? Okay. Yeah, it's really cool. Yeah. Okay.
No more questions?
The idea of feeding the AGN used by inner bars, is there any correlation between the presence of an inner bar and CFIT or an AGN? I think there isn't, in fact.
There isn't, but there are very few inner bars, so we don't know that many. And also the time. Well, you always say that the time scales of all the processes are different, so you don't need necessarily find a correlation.
So, can timer say anything globally about this?
Well,
Will
not
it be
yet,
able to
because
do?
we don't have enough galaxies, but these galaxies have a Hydro. These 2 galaxies have activity. Activity. Yeah. You can look at it, maybe.
Well, okay.
I can tell you later. Yeah, I mean, we are starting the project, so there's still a lot of things to be done. Yeah.
No questions? No more questions? Okay, if you don't have more questions, we can go to the cafeteria because we have the scientific coffee and we can continue the discussion there. Thank you.